Welcome back to the last session for today, and I want to use this time to guide you through the process of taking molecular simulation data into a Jupyter notebook, process it with PyEMMA, and finally feed it to the Thermo API in order to get a multi-ensemble Markov model out of it. If you go to the Dropbox, you should find a directory methane in day 3 with a Jupyter notebook of the same name in a data directory. Please open that. That's where you're going to work in. And everything we're doing here, simulation-wise, is based on this tutorial, which is also referenced in the Jupyter notebook by Wes Barnett, who shows how to use GROMEX by setting up a simple system with one or multiple methane molecules in a water box, but also how to use GROMEX in order to perform umbrella sampling simulations by restraining the center of mass distances between the two methane molecules and to force it to sample along this reaction coordinate. In the data directory you find a number of simulation files, XCC format, which includes still everything, water and the methane molecules. And a bit more, just have a short look at this. In the data directory you have a GROW file, which holds the structure that you need for the feature horizon. You have a single long trajectory, you have a number of short trajectories, MD and then an index. And you have a file meter.dat. Let's look at this in a moment. You have a topology file. You have umbrella sampling trajectories. So, let's go back. We want to do umbrella sampling simulations. That means we are going to exert a bias on our system, which is modeled by a harmonic potential, which is placed on the distance between the carbon atoms of the two methane molecules. As Fabian has shown earlier in the notebook, this is the one-dimensional case, which can easily be extended to a multi-dimensional case. Not important for this particular example. And eventually, you're going to use the estimate umbrella sampling function, which has been shown this morning already, in order to build a multi-ensemble model. Just to repeat it again, this function requires you to provide a number of parameters. A parameter which has a list of trajectories with the reaction coordinates, and a list of trajectories which are the discretized versions of this. And for each element in these lists, you have to specify a center for the corresponding simulation and a force constant that was used for the simulation. This is a bit oriented at the meter file format of the GWAM code. Who has worked with that before? This is one of the most established pieces of software for applying the weighted histogram analysis method. And what they are using is a very simple format of organizing your data, which is here in the meter file. Let's have a look at that. The GWAM code usually reads a file where you specify where all the other files are and which parameters were used. So in the GWAM case, you should have here a file name. I just put an index there. Doesn't matter for our example. You have a spring constant, which in this case is given in kilojoule per mole per distance squared, and an umbrella center, which has a dimension of nanometers. So the simulation with index 0 was performed with this spring constant and this distance restraint on the carbon distances. And while we go through the indices of our simulations, we increase the distance parameter. So step by step by step, we're pulling the methane molecules apart from each other and sampling and restraining the distance that we have specified here with a spring constant of this value. So we're not changing the spring constant along our simulations. So this is a standard syntax for G1, and we try to mimic this a little bit because it's a very easy way to organize your data. You can have several trajectories with exactly the same settings. The software can deal with that. All you need to know is that the let's say first element in your list of trajectories has this spring constant and this umbrella center parameter. This is what you have to feed into the estimate umbrella sampling function here. So the list of your reaction coordinate trajectories, a list of the discrete trajectories, and then for each of these trajectories in this list you have to specify a center and a force constant. Additionally, you can supply trajectories which were not subject to such a bias. We have extra keywords for that because you don't need to set up another list where you say spring constant is 0 and the center is undefined. This is something we can hardcode. So we have separate keywords for your unbiased trajectories. And talking a little bit about dimensionality, units, we assume internally that most of your stuff is already dimensionless. That means your spring constant should be given in values of kt by distance squared. And if you have not such a nearly unitless representation, you can give your actual kt value. So in our case, as the spring constants in gromics, in this case we're treated in used in kilojoule per mole per distance squared, we supply a kt value which actually has units of kilojoule per mole. And then we have treated the units correctly. Then there are a few other parameters you can specify. Max iter is threshold when to stop the iteration, disregarded if you're converged or not. So you don't want to have infinite loops. And this, we found out, could be a bit confusing. This is not the maximum error that you want to have on your results. This is an increment, well, a convergence criterion based on the increment. You're optimizing parameters, you're optimizing a model here, and if the change between your model in one iteration and the next falls below a certain threshold, then we say we're converged. This is by default nearly double precision, and you need that because if you have this, well, let's say 0.1 or 0.01, this looks small, but if you have a high number of small increments, you can still travel a long way. So by not having a very tight convergence criterion in this parameter, you can get arbitrarily wrong results. We have seen that many times before. So this is not a case of a type of error criterion where you say my error on the final result is below the threshold. This is a convergence criterion based on the change of the thing that you want to optimize. You can ask for some information which is recorded during the optimization with this parameter. By default it's 0, it's not recording anything. But if you set this to a positive value, you can afterwards plot how the system converged to its result. You can request a certain type of estimator. By default it's 1 because it's robust, always gives a result even if it's wrong, and it's very fast. We have a lag time parameter which is only used for the TRAM-based estimators. You can specify a time step between your frames that you feed in. And for the expensive methods, dTRAM and TRAM, you can specify an initialization method. So dTRAM by default can be initialized with a WUM estimate, and TRAM can be initialized with an MBAR estimate. So you get a better starting point from which you start your actual expensive optimization of dTRAM or TRAM. And for the initialization method, you can also specify a maximum number of iterations and a convergence criterion. This is rather new. If your reaction coordinate contains something which is periodic, then you need to treat this accordingly. So you can specify here for each dimension of your reaction coordinate with a positive value in a list that this is actually periodic with the given width here. If it's none, 0, or set to something negative, it will be treated as non-periodic, which is the default case. But if you have, for example, a restraint on a dihedral, then you need to specify this with a 2 pi for this part of the reaction coordinate. We will look at a case which is very simple, where your reaction coordinate is a distance, it's one-dimensional, we treat it as non-periodic. But your reaction coordinate can be of arbitrary dimension. So you could say we have a 5-dimensional reaction coordinate, the first 2 are for a dihedral, the other 3 are for something else. And this can be easily given in the force constant in the centers by treating them according to the documentation. And then you can specify additional keywords by which you can influence certain parameters which are unique to certain type of estimator. So TRAM has a lot of small means of tweaking. For example, how to treat overlap in order to get the active set, and others which are not part of the standard estimation, but you can still override them with this parameter. So this is a lot of information. Now let's go over the task for this hands-on session. As I said before, you have a data directory with a meter file, which contains the information of which umbrella sampling trajectory had which force constant and which distance parameter. You have the umbrella sampling trajectories. The asterisk indicates just the number, the index of the trajectory, as given here in the meter file. These are GROMICS generated umbrella sampling trajectories. You have unbiased short trajectories, which are indicated by MD, and then an index. The index does not matter, you can permute them as you want. They are just started from a high energy state at the potential of mean force. And then you have finally a single long unbiased trajectory which you can use to build a normal MSM from. The distances in these trajectories are given in nanometers, the energy is in kilojoule per mole, and the frame stride between is half a pi per second. Now, as a rough guide, what you should do in order to transfer this into PyEMMA and then finally into a multi-ensemble model is look at the meter file again and try to extract this. In the estimate umbrella sampling, you need to specify a list here of the centers in the same order as the trajectories are here given, and you need to specify a list of force constants. Very important, we decided at some point that the top level structure here is lists. So you cannot just say I make a NumPy array of all my force constants and pass it in here, because as I mentioned before, your reaction coordinates can be multidimensional, and this is the point where you can use NumPy arrays to treat the high dimensional case, but on the top level it must always be a list or a tuple. So you need to read in this meter file and separate the stuff into the indices, the force constants, the distances. Then let PyEMMA make some work. So create a featureizer in order to extract the carbon-carbon distance and load all your trajectories. Then discretize your trajectories in a systematic manner. So you could throw all distances, all trajectories together into a cluster of method that works, and then you can separate it again because the order is not changed. And if you know the first 10 trajectories were umbrella sampling trajectories, then the first 10 discrete trajectories correspond to these 10 umbrella sampling trajectories. You could also discretize them independently, but then you need to make sure that every discretization process uses the same centers. The easiest way is to define your centers a priori and then just assign to them, or you do for one of these simulations a clustering, extract the centers, and use then these centers in order to assign all the other trajectories to them. This is what I said meant when I said there are many pitfalls of treating multi-ensemble simulation. This is a very complex topic, and there's a lot of work that you still have to do, even though this is already the user-friendly part. And yeah, if you have the trajectories, you've discretized everything, you can pass it to the umbrella sampling API function. You could run it with 1 as an estimator, or with TRAM, or with DTRAM, or with MBAR. and then you can visualize the convergence process, and you can visualize afterwards the stationary properties of the system. Of course, we're just looking at umbrella sampling data. A very important point about these multi-ensemble methods is you can get stationary estimates for every thermodynamic state, regardless whether you have observation of the state or not. But if you want to have kinetic data, this is only available if you have really sampled it in this particular state. So if you do not feed unbiased trajectories into this function, you can still get a potential of mean force, but you cannot get a Markov state model. You get only Markov state models for these thermodynamic states in which you have observations. Okay, if you have done this for just the umbrella sampling data, repeat it for umbrella sampling and unbiased data and see what's changing. And if you have done this, you can not only compute the stationary properties, but also kinetics. For example, you can visualize implied timescales for the unbiased model in order to see what is a good lag time, and you can also compute mean first passage times. So this notebook is still pretty empty. We have a bit of time, and I indicated a little bit the first steps, what you could do. So try to get the meter data in some variable, and then make lists of your files, for example, which are umbrella sampling files, which are ND files. Extract the spring constants and the distances, the distance restraints from the meter file in some way, and make sure they are stored as a list. And then build your featureizer object and somehow load the trajectories. This is pretty much just repeating what you've already done the last few days. But now you have to put all this together. And once you have done all this, you have a list of your spring constants, a list of your distance restraints, you have a list of the reaction coordinate trajectories for the umbrella sampling and the unbiased case. You have discretized both of these lists of trajectories. Then you can go on and feed this into the estimate umbrella sampling API function. Okay, I have seen already some successful applications of PyEMMA to this particular problem. Let's go over my solution. So, first step, get the umbrella sampling parameters. So I said there's a meter file which you can just load with numpy load txt. The meter file is a selection of columns in ASCII format, so load txt will take this ASCII format and make a matrix out of it. Okay, we have our meter data. The first column, as I said, are the indices of the umbrella sampling trajectories. The second column are the force constants. Third column are the distances. So let's take the first column and loop over all the indices.
Sorry? Can
Yes?
you increase the font?
Sure. At least I hope so. Better?
Okay.
Okay, let's loop over the first column. This is a slicing operation, but I assume most people should be familiar with this. So make a list, loop over all elements in this first column, and take the variable in every iteration and put it in here in the string, and the result is a list of file names. So now we have a list of file names for the umbrella sampling files in the same order as we had the indices in the meta file. This is just Python list behavior. Then we need the spring constants. This is the second column. So we take the second column of our meter data and cast it into a list. The same for the last column. These are the distances. Let's cast it to a list. Now we have effectively gotten the umbrella parameters into these two variables here and made sure that we have all the corresponding trajectories, at least their file names, in the right order in this variable. we also have molecular dynamics data. I don't know how many trajectories there are because I don't have a meter file, so I just use the glob. This enables Python to handle regular expressions in the same way as your bash can do this on Linux. So now we have the meter format transferred into these 3 files, and we have a list of files for the unbiased trajectories. Let's move on to something from the first day. At first we create a featureizer. We call it features. The featureizer needs to know what is our system made of. So we pass the grow file to it. This contains the whole topology information. So we have a featureizer. We want to have a distance of carbon atoms. So we add distances. We add distance calculation to the featureizer, and that needs indices of particles. So we use the featureizer's select method and a string describing what particles we're interested in to get this list of indices. And now the featureizer is able to identify carbon atoms and to tell the source object later on to get for these indices the distance. And finally, you can just describe what the featureizer does. So our featureizer consists of a distance calculation between these 2 carbon atoms here. That's what we wanted to do. Next step. Again, let PyEMMA do the work. First, we define our centers. This can be done by just creating a one-dimensional array of positions. These should be our cluster centers. You could also use rackspace or k-means or whatever to do a clustering, but I wanted to keep everything separate and easy, so I just said, let's do a binning. All the bins which are too far away from observed states are not part of our active set later on. So just use something which is big enough to encompass everything which might be important. So now we have a one-dimensional array containing my proposed cluster centers. Not necessarily a good choice, but a possible choice. Again, let PyEMMA do the work for you. We want to have a list of the reaction coordinate trajectories. So let's make a list. Again, this list comprehension syntax. We make square brackets and we write a for loop inside. So PyEMMA has this nice source function in the coordinate subpackage. The source function requires a list of file names. These are the umbrella sampling file names, which we prepared above, and some information what to calculate, and that is in our featureizer. So by calling this part here, we create a source object which is able to read in all these trajectories and to compute the distances. And it does exactly that if you call the getOutput method of this object. So by creating it and just appending the getOutput method command, this effectively creates a list of all the distance trajectories from the umbrella sampling trajectories in the same order as you have specified the file names. Now this is a list, and I mentioned before that there was this problem with floating point and single precision, double precision. So let's combine everything. If you have a list, you can make a for loop over this list and just cast everything. So what is in here does pretty much the whole work. So loop over all file names, read all the trajectories, compute the distances, and cast the resulting single precision trajectory to double precision, and store the resulting list in US-stars. Looks a bit complicated, but it's quite compact. Now we have a variable containing a list of all the distance trajectories from the umbrella sampling simulations in the right order. And if we pass this list to the PyEMMA coordinates assigned to centers, then it tries to assign every frame in all of these trajectories to the nearest center. So we specify, we supply a list of trajectories and we supply the centers. Unfortunately, PyEMMA assumes that centers always have to be at least two-dimensional, even if they have just one component. So you need to reshape this but this is also something you could put on the list for making PyEMMA easier to use. And now this function takes your list of umbrella sampling reaction coordinate trajectories and discretizes it by assigning it to these centers that we have defined above. We take exactly the same code and do it again, but this time we use the MD file names and just store it to different variables. So we have now MD charts containing all the time series of the reaction coordinate values from the unbiased simulations. And we discretize this as well with the same centers information. And just for the sake of completeness, we load, again with the source object and our right features, the single long trajectory, get the output, and pass this whole thing to the assigned two centers, and discretize it. We don't need the actual distance values because this is not part of what we want to put into the estimate umbrella sampling function. This is something that we just want to build a Markov state model on. Okay, this was quite a long code block, but this is a very critical step. So how do I get my information organized? How do I get my information into the TherMA API? And this, for molecular dynamics data, usually requires to have a solid understanding of the coordinates package. So how do I extract certain features from my trajectories in order that I can compute the bias values? You could always say, I'm using Gromix and Plummet. Plummet writes me my reaction coordinate values out. But if you want to also feed unbiased simulations into your data, you need the reaction coordinate values of your unbiased simulations as well. So you either post-process these trajectories with Plummet as well, or you just learn how to use PyEMMA in order to do this. Questions on this part? Okay, then let's continue. For a start, let's build a Markov state model. Should be known. So we take our long trajectory that we have discretized, feed it into the PyEMMA MSM implied timescale function, along with a number of possible lag times that we want to screen, and Bayes method to compute errors, and restrict ourselves to the first three implied timescales, and see how the implied timescales converge with the lag time. So if we have just unbiased data, long trajectories, we can easily build a Markov state model, and we see that around 20 you are nearly converged, and let's try this. So we take our long discrete trajectory, we build a Markov state model out of it with lag time 20 steps, and we make a Chapman-Kolmogorov test, just use 2 states, see what happens. And this looks reasonable. So under the assumption that 2 states is meaningful decomposition of our big set of states, and lag time of 20 steps, everything is perfectly Markovian. Looks good. But this is old stuff. Let's see what we can do with the TherMA package. Now, we have organized all our data. We have the list of reaction coordinate trajectories and their discretized versions. We have the umbrella centers, the umbrella spring constants. We have a fix for the KT value because they are not dimensionless. And we call this function twice, once for WUM, once for TRAM, with a lag time of 20 steps. And we store the result of each call in a WUM underscore equilibrium or TRAM underscore equilibrium. Just see what happens if we have just the umbrella sampling data. And we also request convergence information. Now, PyEMMA has this nice plotting function for multi-ensemble estimation functions, where you pass a list of all your estimators, so the returns, and this visualizes how everything converged. So in my case, I see that WUM converges quite quickly, so it's easy. But in case of TRAM, the optimization is not exactly as straightforward because WUM operates just on the stationary probabilities, and TRAM operates on a much higher number of parameters. You have transition matrices to optimize. You have Lagrangian parameters in order to satisfy all the constraints. So you have much higher dimensional space in which you work. And what can happen often in these situations is that your optimization does not just decrease, you might actually accelerate again and move faster in your parameter space. You might see that, oh, it looks converged, no, it gets... So you have movement in the optimization. This is a quite common picture that you see for umbrella sampling. Okay, let's see what the results are. Estimate umbrella sampling is a wrapper function for our other estimators like WAM, DTRAM, EMMA, and TRAM in the case of umbrella sampling simulation data. So what this wrapper function does is it creates the bias energies for you. And what it returns is a model and estimator object. And these objects are, in the case of WAM and EMMA, just multi-therm models. So they have information about the stationary properties of your system at different thermic states. And always the information about the unbiased state, whether you have data in the unbiased state or not. This is just reweighting. And this is what we plot here. So on the left side, we plot the stationary distribution of the unbiased state along our reaction coordinate for WAM in blue and TRAM in orange. This is a log scale plot, and these are the free energies in units of kT, also along the reaction coordinate. And you see that you have a small peak here on the side, which corresponds to a small distance between both molecules, which corresponds to a small well here in the free energy profile. And then you have barrier, and you go to the bulk, which is the most probable situation for this particular type of system. So the bound state is not very stable. The stable part would be both are not connected. And this is what you can see just from the umbrella sampling simulations. Okay, TRAM and DTRAM would not only give you the stationary information, they would also give you kinetic information. However, we have done the estimation just for the biased data, so we have no unbiased observations, so we have no unbiased Markov state model. For each thermodynamic state which we have simulated, we have a Markov state model, but these are Markov state models for the biased situation, so you see how the movement inside of an umbrella is. And I don't think this is very informative. So let's go to the case where we have both types of data. We call both functions again. In the case of WAM, we use a different variable to store our result in. And we add this line where we specify the unbiased reaction coordinate trajectories and the unbiased discrete trajectories. Everything else unchanged. In the case of TRAM, we also add this line, but instead of selecting a single lag time, we now, like in the implied timescale plot above for the long trajectory, we give a sequence of lag times, a list. And what then happens is the following. If you have a list of lag times, you get a list of multi-ensemble Markov models back, one for each lag time. And then you can visualize the convergence behavior again. This is how the increment of the internal degrees of freedom changes over time and converges. And this is how the log likelihood increments are happening over the iterations. And you also see that depending on the lag time, you converge faster or slower. And what you can do additionally is you can look at the implied timescale convergence of the unbiased Markov state model. So this time we plot 3 panels. The first 2 panels are used for the regular convergence behavior. The third and last panel we pass to the PyEMMA plot MEMM implied timescales. This is not the regular implied timescales plotting function. It's different because you have different type of data for this. And this computes for every MEMM that you have estimated. So for every row, for every column in this plot. the first 3 implied timescales and visualize how this changes. And you see, if you do a TRAM analysis with different lag times, if your lag times go up, the implied timescales of the unbiased MSM from the TRAM estimation also converge, and still 20 looks pretty reasonable, what you've used before. And again, we can visualize the stationary properties. Now let's select the second to last TRAM model out of our list. This is corresponding to the lag time 20. And plot everything and compare with the long trajectory that we have simulated. And now we get this particular picture and try to understand what's happening there. The green line is the stationary distribution of the unbiased regular Markov state model. And on the right side, it's the free energy profile that you get. And what you see here is it's very unlikely to be in close contact. You have something which is slightly metastable at a short distance, then you have your barrier, and then you go into the most probable area you are far away. But as our cell is of finite size, at some point you cannot get further away before you get closer to an image. So you have a cutoff there. But depending on orientation, you can have a situation where you are somehow diagonal in your box, and then you can have larger distances, but you don't have as many possibilities how you can arrange this. So there's an entropic contribution which makes it unlikely to have these high distances again. So we see that the probability to be at these large distances decreases. You don't have that many space. And this is interpreted here as an increase in free energy. It's just the finite size effect of the box. If you look at the WAM result, you see something which is quite typical for estimators which require global equilibrium. The MD data that you passed into the estimator was really not in equilibrium. These are short trajectories which are just long enough that you can go from the barrier state at which they were spawned either here or there. But they are really not long enough to explore this region enough. They are very short. I think they are 0.1 nanosecond or so. And thus, your statistics, especially in this area, is quite bad. And as they are not in equilibrium, you're violating a crucial assumption in the derivation of WAM. And how WAM reacts on this is it assumes that these trajectories, which are dominantly sampling in this area, are in equilibrium, and so it gives much more weight to these areas as they should have. So WAM overestimates the stationary probability in the area where these trajectories were started. This problem does not occur for TRAM, but still, as the TRAM picture does not explore the unbound state well, the unbiased trajectories were just way too short in order to explore this thoroughly, and the biased simulation, we're just covering the range to here. What you have in this area is statistically quite bad. And this is something that you have always to keep in mind when you're setting up your simulations. If you can make sure that you have unbiased simulations which explore these probable areas well, that's fine. Then you can just add short regions of bias areas to enforce the transition over high barriers, for example. But if you cannot make sure that your unbiased simulations can explore everything which is important, then you need to make sure that your biased simulations cover that. So this is one critical pitfall. And yeah, this is stationary data. Let's look at kinetics. For the kinetics, I said take the MSM and take the TRAM estimated MSM and separate everything in two states. So I make cutoff at a distance of 0.55 nanometers around here at the barrier, and every state, every Markov state that falls to the left is state 1, every Markov state that falls to the right is state 2. See what happens. And then we compute for the MSM and the TRAM-based MSM, mean first passage times between these two states. They are in perfect agreement for the fast process, which is going from this side to this side. This is very short. This is well sampled. This is easy. But going the other way around, this differs quite a lot, which is also not surprising given the amount of data that we actually had, and given the situation that the MSM explored this region very well, while TRAM just explored to the area of the transition of the umbrella sampling range, and then had a little bit of crossing of the unbiased simulations into this area, but did not sample it well. So the time scales, the mean first passage time that you compute, also depend very much on good unbiased data. So if you want to fix that, you should not only spawn simulations at the barrier region, but also maybe some unbiased simulations in this area. So there are always ways to fix this by just adding a little bit more, more data. But I completely forgot what I wanted to say. Okay. But you should not just put biased and unbiased data together and always assume that you have a good result. You always have to be a bit critical about what you're doing and trying to understand what's going on in your system. Okay, that was everything for this notebook. Are there questions on this?